Okay, welcome to part 2 of the NMR Spectroscopy lecture. All right, let's talk a little bit about the third important piece of information you can get from an NMR spectrum, which is the integration. And the integration stands for the area under the curve. So basically, the computer calculates the area under each signal and converts that area into a step curve, which is what you're seeing with these red lines here. And then it will randomly assign values to each one that are meaningless but relative to each other. So what the user has to do is go ahead and figure out what these random values relate to. So typically, if a user didn't know what they were looking for in an NMR and wasn't sure what the peaks probably stood for, they might take the one that integrates for the lowest value, which in this case would be 27.0, and then arbitrarily set that equal to 1 and see what happens to the other values as they're reassigned based on that being set to 1. So divide all of the numbers by 27. Oops, let's go full screen here. Divide all the numbers by 27 and you get 1 to 1.48 to 1.05 to 1.56. So what we're looking for is whether or not these are whole numbers or very close to whole numbers, because there's always some error associated in these calculations. So what we see is that we are not looking at whole numbers, because this is close to 1.5 and this one as well. So what we can do is multiply by a number to get whole numbers for all of them. So what we could do is multiply each number by 2. So if I instead change that to 2, then relatively we have 2 to 3 to 2 to 3. And the reason why these have to be whole numbers is because these are representing hydrogens in a molecule. And of course, you can't have half a hydrogen atom in a molecule, so you have to have whole numbers. So once they're really close to whole numbers, you're probably at the relative integration ratio. Please note that this might not correspond to hydrogens. So what you need to do here is double check, if you're given a molecular formula, double check that the total integration matches the molecular formula. Remember, we're looking at hydrogen atoms. So it's 2 plus 3 plus 2 plus 3 is 10. So we would want to double check whatever molecular formula we're given has 10 hydrogens. It could have 20 hydrogens, in which case there's some symmetry, and the real numbers are 4 to 6 to 4 to 6, which is also possible, but less likely. So just remember that integration values are relative quantities rather than absolute count of the number of protons. So sometimes the lowest common number, where everything is a whole number, might not be the actual number of hydrogens in some cases, because symmetry can affect integrations. For 3-pentanone, we would get 2 signals, one for the 2 methylenes and one for the 2 methyls. And the lowest whole number ratio is 2 to 3, but those actually represent 4 to 6. So that's when you need to figure out if 2 plus 3, which equals 5 hydrogens, matches the molecular formula, but the molecular formula says H10. So it doesn't match. That means that there must be some sort of plane or rotation of symmetry to allow for a higher ratio, like 4 to 6. So for example, the NMR of that compound would look like this, right? Integrating it would give you 2 to 3, but it's really 4 to 6. So always compare the total integration with the molecular formula to see if there's a plane of symmetry. Okay, let's talk about the last important thing to look for in an NMR spectrum, which is called the multiplicity, also known as the splitting pattern. And the splitting pattern actually tells you about the neighbors in a molecule, which is really important for putting the piece of the puzzle together. Because it's really nice to know different hydrogen groups, but what are they next to is crucial for being able to come up with an entire structure. So first, when you're looking at the signals, we would want to see, is there one single peak? We call that a singlet. If there's two that are about equal height, we call that a doublet. If there's three, this will be in a 1:2:1 ratio. We call this a triplet. Quartets are 4 peaks in a 1:3:3:1 ratio, and so on. Okay, so quintet, sextet, septet. I think there's a table in the book that talks about the relative values of the peaks in these, but you're just counting up peaks and to determine what the pattern is. And that's the first step. And then just recognize that multiplicity or splitting patterns come from the presence of nearby protons. So let's explain why that is. So let's consider in a molecule there might be 2 neighboring protons called HA and HB. Well, what we know is that, let's think about HA, right? HA has a proton in its nucleus. That proton is creating a magnetic field, right, called the magnetic moment. And what about HB though? HB's proton is also creating a magnetic field, and when in the presence of an external magnetic field, both A and HB will align either with or against the magnetic field, and independent of one another, right? So let's think about what it would mean if HB is aligned with or HB is aligned against the external magnetic field. Well, these are close enough where the tiny little magnetic moment produced by HB affects the overall magnetic field felt by HA. Because if HB is aligned against the magnetic field, like this, right, then that's actually going to shield HA a little bit. And if HB happens to be aligned with the external magnetic field, so this is like alpha state, beta state, right, that will de-shield HA a little bit. So the magnetic moment that HB possesses, either with or aligned against the external magnetic field, actually will affect the frequency that HA absorbs, because HA is either randomly a little bit shielded or a little bit de-shielded by the presence of HB. So I don't actually like this picture, but it does come from your book. The reason why I think it's confusing is because aligned against the field is drawn on the left, and aligned with the field is drawn on the right, but they should be switched. And the reason for that is aligned against the field shields HA a little bit, which we know should make the peak come a little bit more to the right on the NMR spectrum, so it should be this one. Aligned with the field makes it feel an enhanced field, which de-shields it, which is responsible for the peak splitting to a little bit more to the left. So I think these two imply these two, but it's actually switched. Hopefully Klein will fix that in his 4th edition of the book. So as a result of HB being a neighbor, the peak for HA is split into 2 peaks, right? Each one would be about half of the area under it that it would have been had it not been split. So it's like splitting one peak that would have come in the very center of these two and been twice as high into 2 peaks slightly to the left or slightly to the right, right? And it's all because of the neighbor nucleus of the hydrogen atom either shielding or de-shielding the magnet for HA. Let's think about what would cause a triplet. A triplet is caused when there are 2 equivalent neighbors on a carbon next door, also known as an adjacent carbon. So we're still looking at the signal for HA, but now there are 2 neighbors, right? 2 HBs. Each one can be aligned against or with the external magnetic field, right, when the external magnetic field is applied to the molecule. So what are the probabilities? Well, there's the probability that they're both aligned against, right? And then there's the probability that they're both aligned with. And in the middle is the probability that one of them is aligned with and against. Since there are two of them, we can either have with and against or against and with. So there's four basically possibilities for the combination of the two magnets in HB and their effect on HA. So that creates a 1 to 2 to 1 ratio of signals. The signal in the center, right, this one here, is actually not shifted at all. Because if you have a neighbor who's aligned with and a neighbor who's aligned against, overall that's no net effect. So it's not shifted at all. But the when they're both aligned against, that would produce a signal that's shielded, so the one to the right. And when they're both aligned with, that deshields it and produces a signal a little bit to the left. So whenever HA might have two equivalent neighbors, it will have a, it will look like a triplet because of its neighbors. Okay, what happens if HA has three neighbors, all called HB because they're all equivalent? What are the probabilities, right? Well, all three could be aligned against, all three could be aligned with, and then even more probable would be two aligned against, one with, or two aligned with, one against, right? And this is the different situations that can occur. And these all have the same net effect, right? So it becomes a signal in a 1 to 3 to 3 to 1 ratio. But because there's four peaks, we call it a quartet. Again, these are a little bit switched. So super aligned against is shielded, the one to the right. Super aligned with is deshielded, the one to the left. Technically, this has a net deshielding and a net shielding effect, which would move the original peak a little bit to the left and the right. So three neighbors means you get four peaks called a quartet. Are you starting to see a pattern? Okay, so you can look in the book and there's a table that talks about how the multiplicity trend continues. And what you can do is analyze the splitting pattern when you see a signal in the proton NMR, assuming it's a simple pattern. Again, some signals don't produce a simple pattern. But if it's a simple pattern, then you can analyze it to determine the number of equivalent protons on adjacent carbons. And what we do is we use what's called the n+1 rule, which basically says that n is the number of neighboring protons, and therefore you will get n+1 peaks in the signal. So just remember that if you see a triplet, right, that means that there were two neighbors. So it's one less neighbors producing the signal. So if you see a doublet, there's one neighbor, right? If you see a singlet, there are 0 proton neighbors, etc. Okay, so there's some key rules to know about for splitting. The first one is that equivalent protons cannot split one another because they resonate together. And which means that if you have two hydrogens at the same carbon and they're equivalent, you're not going to, this is not a neighbor, right? They're not neighbors of each other. They're just the same thing. So to split each other, protons must be within a 2 or 3 bond distance, right? So they have to be most commonly vicinal, which basically means on adjacent carbons. I always think of this as in the vicinity, right? So kind of close together. Or geminal, but only, and geminal means attached to the same carbon, but this is only possible when you have diastereotopic protons. So diastereotopic protons are protons that are two protons attached to the same carbon, so part of a methylene that's next to a chiral center. In that case, these would not be equivalent and they would split one another. Generally speaking, this bond distance that you see on over here to the right is too far apart. So basically, it doesn't really matter if you field, it's too far away to shield or deshield HA. so we don't generally see splitting, but you can sometimes see it depending on the exact conformation of the molecule, and it is called long-range splitting. It's possible to see. It's usually, the peaks are usually very close together when that happens, so it can be difficult to see unless you have a very powerful magnet, so an NMR that is 400 or 500 megahertz at least. Okay, so the n+1 rule only applies to protons that are equivalent or have identical coupling constants. So basically the question is, can you have neighbors on both sides and still use the n+1 rule? Like, for example, if you have a CH2 and it's got 2 neighbors on one side because there's another CH2, and then it has 3 neighbors on the other side because it has a methyl next to it. Think about like the middle methylene on a propyl group. Can you just use the n+1 rule to determine the multiplicity? Meaning I have 2 hydrogens on one side that are neighbors and 3 on the other side. That's a total of 5. If I use the n+1 rule, I should see 6 peaks or a sextet. And with simple alkyl groups like a propyl group, the answer is yes, it does work that way. You can add up hydrogens or protons on both sides, even though they're not equivalent, and use the n+1 rule. But that's only because the protons on both sides split the middle protons to the same magnitude. And therefore, it's a simple pattern. And we're going to go ahead and look through an example to prove how that can happen. If for some cases, there will be some cases where the hydrogens on either side are not very similar at all, in which case the magnitude of the effect of splitting on the neighbor is not going to be the same, in which case you cannot simply use the n+1 rule, and that causes what we call complex splitting patterns, which we're going to talk about. So for example, this structure here, you see the hydrogen in red. If we think about the signal for this, right, we've got one neighbor on the left, that's the hydrogen pointing back, and we have one neighbor on the right, that's the hydrogen attached to the sp2 hybridized carbon, neighboring the carbon attached to the proton in red. So there's 2 neighbors, right? So will we simply say, okay, 2 neighbors plus 1, I'm going to see a triplet? Unfortunately, probably not in this case. And the reason for that is the hydrogen on the left and the hydrogen on the right are not similar, right? They're in a very, one is attached to an sp2 hybridized carbon, the other is attached to a chiral center. So as a result, they're probably not going to affect that central red hydrogen in the same way. So that creates what's called complex splitting. But first, let's talk about what we need to, some definitions, some things that are important when looking at splitting patterns. Okay, the first thing we want to talk about is what's called the coupling constant, or the J value, okay? And that's the distance between the peaks in a signal that has multiplicity. So for example, in blue here we see a quartet, in pink here we see a triplet. We can measure the exact distance between all of the peaks here. You can see where it says JAB and JAB in both of those. And the NMR will allow you to do some peak picking, where we can get the exact chemical shift of all of the different peaks in the signal. And then the difference between them, so for example, let's say this is we're going to do, I'm just making up numbers here, 4.00, just to make it really easy on myself. And then this one is 4.07, okay? So the difference between those is 0.07. I take that, multiply it by 100, and that gives me the coupling constant, which is 7, and that is in hertz. So the coupling constant, or the distance between those, is 7 hertz. Okay, so that's the simplistic way to just calculate it directly from chemical shift values. Okay, one of the things that's important here is when you measure these coupling constants, In order for these two to be the result of neighboring protons, the coupling constant has to be the same, because the magnitude of how A affects B should be equal in magnitude of how B affects A, right? If one is the neighbor of one and the other one is the neighbor of it, right, then the coupling constant or the magnitude of the effect should be the same. So that's the first thing. JAB must be equal to JBA, right, for these two to potentially be from hydrogens that are neighbors of one another. So the good thing is that the coupling constant is pretty much the same for all hydrogens in an alkane. It's going to be around that 7 hertz. So that's very easy. But there are some that drastically are different from that. Some that I might want to highlight are like the alkenes here. We can see the relationship between the effect of neighbors where protons are trans to one another, where they're cis to one another, and then where they're geminal. So these two split each other because they're non-equivalent, okay, or when they are non-equivalent. And look at the difference in the J value. They're very, very different. This can be very helpful because sometimes we have alkenes in our structure and they might be cis or trans, or they might be E or Z. And so it can be very helpful to measure coupling constants to see, okay, I've got these protons. They're clearly protons attached to the alkene carbons because the signals come in the range of 4.5 to 6.5 ppm for chemical shift. And if I measure the distance between the peaks, right, I can usually tell the difference if it's going to be a trans alkene or a cis alkene, which is very helpful. Aldehydes have a very small coupling constant with neighbors, and these are some for the aromatic ring, but this is not particularly important. Okay, one thing to note is that coupling constants are the same because they're in hertz, and it's a difference between two peaks, regardless of the operating frequency of the spectrometer. So no matter if you're using a 60 megahertz or a 500 megahertz instrument, when you measure the coupling constant, it will be the same number, which is helpful. Okay, let's talk about the difference a little bit though in the spectrum. If you take the NMR on a 60 megahertz spectrometer or a more powerful 300 megahertz spectrometer. I told you before that the more powerful magnets produce better peak resolution. So for example, what you can see here is it's the same signal, right, run on two different instruments. For the quartet here, like look at this CH2 group, it has 3 neighbors, so using the n+1 rule, it would be a quartet, right? In the 60 megahertz instrument, you can't exactly see the 4th little peak here in the quartet because it happens to overlap with the signal from labeled C, which is this CH2 over here. That's a singlet because it doesn't have any neighbors. But in the more powerful magnet, you can see the peaks are very resolved. So that is the main reason why people want to have a powerful magnet. It is easier to see signals that are resolved from other peaks. So you can, it makes analysis of the spectrum that much easier. The way I think of it is if you take, for example, the divisions between 4 and 5 on the x-axis, so in chemical shift or parts per million. What you can do is break this up into 60 pieces if you're using a 60 megahertz NMR, and you can assign signals to those 60 pieces, right? But if you take the same one chemical shift range of 4 to 5 and you use a 300 megahertz instrument, you can break it up into 300 equal slices. And you can assign values to any of those 300 different equal slices. There's just more to go around here, so the likelihood that they will have the same exact value, RF value or radio frequency value that it absorbs, is a lot smaller when there's a lot more resolution or a lot more, pieces of the pie, so to speak. Okay, here's some helpful hints for analyzing spectra. These are super important because it's going to help you do it faster. And speed is a thing, right? Because when you're taking a quiz or a test, you have a limited amount of time. So if you're too slow at this, it's going to be a little bit of a problem. So one of the things to do is just practice, 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 so you're a lot faster. And recognize these patterns, right, is a real helpful thing to do. Okay, so if you see a quartet triplet pair here, and the quartet is usually a little bit downfield of the triplet, it'll integrate for 2 hydrogens. And you also see a triplet in the same spectrum that integrates for 3 hydrogens a little more upfield. This is very characteristic of an isolated ethyl group. Isolated means that R here does not contain any proton neighbors, right? So that it's simply, these are the neighbors of the blue are the neighbors of the red, and the red are the neighbors of the blue, and the blue doesn't have any more neighbors, so it's isolated. The only thing I don't like about this picture, and I would change, is that if this quartet integrates for 2 hydrogens, and it's split into 4 peaks, it should be a lot smaller than the triplet that integrates for 3 hydrogen and is only split into 3 peaks. So it's just relative size, kind of shrink this quartet or grow the triplet so that it would appear more as it normally would in a spectrum. Okay, remember that the coupling constant, or the distance between the peaks, that J value, has to be the same, right, in each signal for them to potentially be neighbors. So if this is your quartet, right, that is definitely not the neighbor of this triplet, because the distance between those peaks is very different. What are some other patterns to look for? Really, really diagnostic, you should pick it up very quickly, is if you see a singlet that integrates for 9 hydrogens, right? How else are you going to realistically get 9 equivalent hydrogens? The most common way to do that is through a tert-butyl group. Is it possible another way? Yes. If there was multiple planes of symmetry in the molecule, you could possibly get that. But the most common way by far is a tert-butyl group. And this is usually a signal that's pretty upfield. And the reason for that is it's at least 2 bonds away from anything electronegative. So it's not usually shifted very downfield. Hold on a second, I gotta let my cat out. There you go. Sorry. Okay, and the last signal that you want to look at, or characteristic set of peaks, is a septet and a doublet. And specifically, that septet will be pretty small. You can see this is kind of the blown up version of this, and it only integrates for 1 hydrogen. And the doublet will be pretty big because it integrates for a total of 6 hydrogens. So when you see this septet doublet pattern, right, or 2 different signals in your spectrum, then what you want to think is isolated isopropyl group, right? Isolated meaning R does not contain any atoms with a hydrogen attached to it. So those are some really, really common signals that will make it easier for you to come to a final answer more quickly if you recognize them. And the best way to recognize them is to practice. Okay, let's talk a little bit about complex splitting. It results when a proton or set of protons, which in this case we're talking about HA, has 2 different kinds of neighboring protons with different coupling constants. So for example, we've got protons are neighbors on both sides, and the effect that they have, or this amount that they split HA, right, the distance, the coupling constant, is different. So if that's the case, then we won't see a simple quartet. However, if the coupling constant is the same, meaning JAB is equal to JAC, then you will see a quartet. So depending on what the coupling constant is between A and B and between A and C, we actually have 4 different possibilities for what the signal might look like. Obviously, and when you see them, you're going to see that they are more complex than normal splitting patterns. Okay, so the first thing to keep in mind is that we're talking about the signal for HA, right? So B are the neighbors and C are the neighbors that are splitting HA. And C will split A into a doublet because there's one C, right? And because there's two HBs, that splits A into a triplet. Okay, so you're either going to get what's called a triplet of doublets, a doublet of triplets, right? We're going to talk about how it's possible to get a multiplet and then a simple quartet. So we're going to go through these four different possibilities based on coupling constants from B affecting A and C affecting A to look and see what could A look like, the signal for HA? And there's four possibilities. All right, so let's look at the first possibility. If JAB, right, which means the distance, right, between the peaks as a result of B splitting A. So if JAB is much greater than JAC, then the signal will appear as a triplet of doublets. So let's see how we can draw a splitting tree that will be able to help us figure out what the signal might look like. So first we start out for the signal for HA. Remember, there are two of them. That doesn't matter. That just means that the total integration or area under the curve will be a relative value of 2 compared to the other signals. So the peaks are a little bit taller, right, because they integrate for 2 total hydrogens. So it doesn't really matter that there's 2 HA. They both are equivalent. So they produce the same signal, right, which we call HA. If it didn't have any neighbors, it would just be a singlet that we are arbitrarily setting as sort of, oops, let's go back, as this level here. And then what I did is I said, okay, this is the possibility where JAB is much greater than JAC. So I did some make-up numbers here. I just made these numbers up, okay? So I said JAB is much greater. So I set that equal to 16 hertz. JAC is a lot less than JAB, so I just randomly chose 6 hertz. Okay, these numbers could vary a little bit. The goal is just that this is much larger than this. And then I drew a splitting tree. So I usually start with the largest coupling constant. Okay, so that would be JAB. Remember that there are 2 Bs. So this is splitting A into a triplet because there are 2 of these. Right, so I split this signal into a triplet. Remember that the center peak in a triplet is the same exact chemical shift, right, of the original. It hasn't shifted at all because that's the situation where one is aligned with, one is aligned against, or and vice versa. Okay, so we have splitting it into a triplet means drawing a line straight down and one to the left and one to the right. Okay, and the distance between the peaks is 16 hertz because that's the coupling constant, which is measured as the distance between the peaks. And then what I can do is split each of those peaks in the triplet further because still those A is affected by C and C is splitting A into doublet. So I can take each one of these and split it into a doublet. Recall that with a doublet, we are not having a peak straight down the center. Only one to the left and one to the right, right? Because we split this peak into 50-50. And the distance, again, between those peaks should be 6 hertz. Okay? And 6 hertz here and 6 hertz here. Recall that the triplet ratio is 1 to 2 to 1, and the doublet ratio is 1 to 1. So this should be a 1 to 1 to 2 to 2 to 1 to 1 ratio, which is why I drew these a little bit taller in the center. Right, so you would get this 2 peaks about the same height, twice as high, more peaks in here. And we call this type of signal a triplet of doublets. The way I think of it is there are 3 doublets, right? And this looks like 1, 2, 3 doublets. So a triplet of doublets. And a triplet of doublets is a complex splitting pattern. Let's look at another possibility. Possibility number 2 is the exact opposite of possibility number 1. Perhaps JAC is much, much greater than JAB. Let's see what would happen. So we can just change those values, right? Maybe JAC is 16 hertz and JAB is 6 hertz. So again, it doesn't really matter. It works out the same either way, but I can start with the largest coupling constant first, right? Recall that there's only one C, so I'm splitting HA into a doublet with a coupling constant of 16 hertz. That splits this into a 1-to-1 ratio because it's a doublet. After that, I can split these new signals into triplets. So each one can be split into a triplet. Remember that you go straight down for the center one and to the left and to the right, and that now you have the measurement between peak 1 and peak 2 and peak 2 and peak 3. And each of those should be equal to 6 hertz. So now you get a, and again, this is it was split 1-to-1, and then it was split in a 1-to-2-to-1. So it looks like a little triplet over here and a second little triplet over there, or what we might call a doublet of triplets, which is like 2 triplets. That's how I remember it. What's possibility number 3? This is actually maybe the most complex one. What if the coupling constant between A and B is similar, but not exactly equal to the coupling constant between A and C? Then, unfortunately, the lines may overlap. And because it's not a simple pattern, oftentimes we just call it a generic multiplet. A multiplet is just a series of peaks that doesn't have a simple pattern. So by default, it's called a multiplet. Okay, so if JAB is similar but not equal to JAC, perhaps JAB is 6 hertz and JAC is 8 hertz. They're similar, right, but not exactly the same. So I can start out with the larger one. Remember, there's only one of C, so I'm splitting HA into a doublet with the difference between the peaks of 8 hertz. And then I'm splitting each one of these into a triplet where the distance between the signals here is 6 hertz. So 6 hertz here, 6 hertz here. For this one, between here and here is 6 hertz. Between there and there is 6 hertz. So this was initially split into 1-to-1 and then 1-to-2-to-1. So it becomes a 1-to-2 to 1-to-1 to 2-to-1, right? And there is there's no name for this in terms of a pattern, so it's just generically called a multiplet. That's a possibility. Possibility number 4. What if, by happenstance, even though they're totally different types of protons, A and B, what if their coupling constants are equal? What if the magnitude of how C affects A and B affects A are the same? We'll actually get a simple quartet. In that case, this is like using the n+1 rule. We've got 2 neighbors on one side, 1 neighbor on the other side, that's 3 neighbors. We use the n+1 rule to predict a quartet. That only works with non-equivalent neighbors when the coupling constant is the same, is identical. So let's see, what if JAB and JAC are both 7 hertz, right? Then we can split HA, you can split it into a triplet. This would be JAC. Oh, I just realized that I believe C is, there's only one C, right? Yes, so I actually labeled this one wrong. This should be JAB equals 7 hertz. Because if we're splitting it into a triplet, then it's the one where there's 2 neighbors, which is B. So I apologize. This is JAB equals 7 hertz. And then split each one of those into a doublet. This would be JAC equals 7 hertz. And because this is 7 hertz, right, and it's split into 3.5, and from here 3.5, right, and 3.5 this way, 3.5, and exactly 3.5. These signals overlap, right? So this was a 1-to-2-to-1 ratio, which is all split into 1-to-1. So 1-to-1 is 1-to-1. 2 here would be 2-to-2, and 1-to-1. So sum of 1-to-3 to 3-to-1, which is how we get the 1-to-3 to 3-to-1 signal height for a quartet. Okay, the good news is the book's example for complex splitting is honestly very unlikely to be complex because it's just a propyl group. And it talks about the different possibilities for HB, but realistically, you're going to be able to just use the n+1 rule because the magnitude of how C affects B and how A affects B will be the exact same because it's just a simple alkyl group. So we'll be able to add them up just like the last possibility and use the n+1 rule, even though A and C are not all equivalent, right? This is equivalent and those two are equivalent, but C is not equivalent to A. Even though that's the case, if they have the same coupling constant, they act as if they're equivalent, and we're able to use the n+1 rule. So this will produce, with 5 neighbors, a sextet for HB. Let's talk about some labile protons, like the hydrogen attached to an oxygen in a hydroxyl group or an alcohol group. So you might look at ethanol and go, okay, wait, there's a hydrogen attached to the oxygen, and then attached to this carbon are 2 hydrogens. Aren't those neighbors to one another? And the answer is yes. However, even though they're neighbors, they don't split one another. So splitting can break down when you're looking at nitrogen attached to hydrogen or oxygen attached to hydrogen. Even when you have neighbors, they don't necessarily split one another. So let's, for example, look at the spectrum here for ethanol. What we see is a quartet that integrates for 2 and a triplet that integrates for 3 hydrogens. That's almost like an isolated ethyl group, right? Like this ethyl group, as if these 2 hydrogens didn't have any neighbors. And then separate from that, we see a singlet that integrates for 1 hydrogen, which is actually for the hydroxyl proton. So even though these hydrogens are neighbors, they don't split one another. Why is that, right? And this is going to happen again with NH or OH, potentially. And for most alcohols, the signal is observed between 2 and 5 ppm, but this can vary. This is one of the type of protons that really can potentially move all around the spectrum, depending on the structure. So it's not a very set chemical shift. What is the reason why we don't see splitting between those neighbors? The reason is because, as I mentioned before, that hydrogen is labile. What does that mean? That basically means that if you have trace acid or base in solution, then there can be a series of proton exchanges between the acid or the base and the hydroxyl group, where it's either protonated and deprotonated or deprotonated then protonated, depending on if it's acid or base. And as a result, any given hydrogen is not spending all of its time around the oxygen. And this is happening so fast, these proton transfers in solution are happening so fast that it's too fast for the time scale of an NMR. Remember, the pulses take several seconds. So we pulse and it has to absorb the energy and then release it. That's several seconds. In those several seconds, those protons have moved all over the place, right, between lots and lots of molecules. So as a result, they are not really there or attached long enough to actually have a magnetic field that affects its neighbors, right? And so it can create this like shielding, deshielding blur, essentially, that can create some peak broadening, especially if there's a lot of hydrogen bonding going on, or it can create a situation where there's no splitting observed. However, if you do get an absolutely pure sample of ethanol, meaning there's no even trace, even the smallest amount, there's no acid or base present whatsoever, it's rigorously purified of any acid or base, then you can see splitting between the hydrogen on the oxygen and its neighbors. It will actually be around long enough to split its neighbors. It's only when this acid or base is present that this rapid exchange of protons is occurring and we don't actually see splitting. And again, broadening is because the length of the oxygen-hydrogen bond varies quite a bit with hydrogen bonding. And that creates a situation where the RF frequency is a little different and it broadens the frequency that gets absorbed and we can see kind of a broadened peak, very similar to IR for the OH signal. Okay, let's look at 3 different isomers of xylene or dimethylbenzene. You might think it would be very difficult to distinguish, like if I know I had a xylene and I didn't know which one, and I took an IR spectrum of one of them, maybe I had this one, right? And I wasn't sure though. Could I really tell the difference with infrared spectroscopy? The answer is no, because they all contain the same bonds, right? There's not different types of bonds in one than the other. So it'd be very difficult to distinguish. Maybe if you had a unique fingerprint region, you could tell. But beyond that, it would be very difficult to distinguish. Also with mass spec, all 3 of these isomers obviously have the same mass. So you're not going to be able to distinguish that through mass spectrometry either. However, with proton NMR, they're very easily distinguished. And that's because of different symmetry operations, creating a different number of signals. You can split this one right down the center, and as a result, you're going to get 1, 2, 3 signals, where these are equivalent, those are equivalent, etc. You can split this one right down the middle here. You'll get 4 signals. By the way, this is called orthoxylene. 1, 3 positioning on a ring is metaxylene. And then paraxylene, where they're opposite, this actually only has 2 signals. And that's because there are multiple symmetry operations. You can split this one right down the middle, and you can split it horizontally as well. So as a result, all 4 aromatic protons are equivalent, and the 2 methyls are also equivalent, so only 2 signals. So each isomer of xylene, while easy to distinguish using an NMR, would be very difficult to distinguish through other characterization techniques that we've learned prior to this week, including IR and mass spec. Okay, so when you get a spectrum, what are the steps that you can take, right, to determine the structure from the spectrum? First of all, you will always be given a molecular formula along with the spectrum. So when you have that molecular formula, you can go ahead and calculate the degree of unsaturation, also known as the hydrogen deficiency index, just like we talked about previously. That again will tell you how many potential pi bonds or rings might be in the compound, which is useful information, obviously, if you're trying to determine a structure. Next, you want to consider the number of NMR signals and the integration. So if you count up the integration for all of the signals, right, and you see that it matches the molecular formula, then there isn't any additional symmetry that we need to worry about. But if you see very few NMR signals, given the number of supposed hydrogens are in the molecule based on the molecular formula, then you need to, again, compare the integration to the molecular formula and think about potential symmetry in the molecule. Symmetry is how you get hydrogens attached to different carbons equivalent. Okay, step 3, analyze each signal and draw fragments consistent with each signal. So the way I like to do it is I look at a signal, I start with the integration. If it says it integrates for 2 hydrogens, I write CH2. If it says it integrates for 3, I write CH3. If it's 1, I write CH, right? And then if it's more than 3, then perhaps there's an isopropyl or a tert-butyl or something. I would consider some of those characteristic patterns we talked about earlier. So start by analyzing the signal, look at the integration first. Draw a little fragment like a CH2 or a CH3 based on the integration. Next, I look at the multiplicity or the splitting pattern. Say, okay, my CH3 that I drew, because the signal integrated for 3 hydrogens, is a singlet. That means it doesn't have any neighbors, right? So I think, okay, I can't have a CH2 next to that. Then I look at the chemical shift, and I think about what is it likely next to given the chemical shift, right? If it's around 2, maybe it's next to a carbonyl. If it's around 2.5, maybe it's next to an aromatic ring. If it's around 3.5 to 4, maybe that CH3 is directly next to an oxygen. So I start getting information about what it could be next to based on its chemical shift. So I start trying to draw these little fragments for each signal, and then I attempt to assemble the fragments into a complete structure, and then just double check that my complete structure actually would match. And the thing that students do is they double check that it matches the splitting pattern, and they double check that it matches the integration, but they forget to double check that it matches the chemical shift, right? Because it's really easy to draw an isomer of the correct answer. And the only difference between two potential isomers that match everything else is the chemical shift. So that's usually the thing that you want to double check when you're doing step 5. So we're going to do 2 practice problems in this video just to illustrate the process. And then I'm going to upload another video that goes through many more practice problems. And then the activity is going to take you through many more practice problems. So the idea is just to get tons and tons of practice with solving the structure of a compound based on given the NMR and the molecular formula. Okay, so I would like you guys to go through the 5-step process, pause the video, and do the best you can, right? Start by calculating the HDI. Think about what that might mean for clues for the structure, right? Consider the integration and see if it matches the formula at step 2. Analyze each individual signal, starting with the integration. Next, draw in neighbors. Next, draw in things that it might be attached to based on chemical shift. To draw a little fragment for each signal. Then try to assemble that into a complete structure and double check your work. This may take you a while, particularly in the beginning when you are new to doing this. The more practice you get, the faster you will become at this. Don't forget about your characteristic patterns, right? Your isolated ethyl, isopropyl, or tert-butyl groups. That will help you do it quicker. Okay, with all of that, go ahead and pause the video and do your best. All right, let's go over the answer. So in step 1, I calculated the HDI according to the formula, and I got 4. Right, so 4 tells me maybe I have an aromatic ring because we have 1 ring and 3 pi bonds. So that's one easy way to get to 4 pretty quickly. Then I consider the number of NMR signals in integration to get clues about the structure. Well, there's not too few, right, signals, so I'm not going to worry too much about it. I am going to count up the integration. So 2, 4, 7, 9, 12. So that actually matches my formula, H12. So I'm not worried about too much additional symmetry. So I know that these are actual ratios of equivalent protons as opposed to having to multiply and it's 4 to 4 to 6 to 4 to 6. It's not that because the number of hydrogens matches the formula. Now I'm going to move to step 3, which is the one that should take you the longest, right? Analyze each signal and draw fragments. So you can work from left to right or right to left. It doesn't really matter. One of the things that I immediately recognized when looking at this spectrum is this quartet that integrates for 2 hydrogens and a triplet that integrates for 3 hydrogens. And I remembered when I have those 2 signals, this could be an isolated ethyl group. And so I drew these fragments really quickly based on that. I looked over here at this next signal at around 3.8 ppm. And first thing I do is look at the integration. So it integrates for 3 hydrogens, so I wrote CH3. And then I look and see that it's a singlet, so it doesn't have any neighbors. So I'm definitely not thinking about having like a CH2 or anything next to it. No neighbors, right? And then I look at the chemical shift and I see, it's between 3.5 and 4. That usually means it's next to something electronegative like an oxygen, right? I look at my formula, I go, I do have an oxygen. So I'm going to go ahead and put that right next to the methyl. This would make this signal downfield enough to match, right, the chemical shift. So I have this little fragment as a result of that. And then I look over here at the signals that are at around 7. Light bulbs went off in my head, and I said, oh my gosh, I've got signals around 7. That means that I likely have an aromatic ring. So my thought about the HDI from before seems to be correct. I probably do have an aromatic ring, which means I don't have any other pi bonds or rings, because this takes into account all of my unsaturation. And then I look and see, okay, when I have an aromatic ring, one of the simplest patterns, and actually really common pattern observed, is when you have 2 doublets that integrate each for 2 hydrogens. This is very characteristic of a para disubstituted aromatic ring, right? So one of the things I like to look at is the integration. There's 4 hydrogens total. That means I should draw 4 hydrogens attached to my ring, and that these groups are something else, not hydrogens. And they're para, which creates some symmetry, right? Which means that these blue ones are equivalent and the red ones are equivalent. So I drew this little fragment. So putting all of that together, that got me para-ethyl anisole, which you don't need to know the name of it, but that's the name of it. So that's what I came up with as the structure. And then I can go ahead and double check all of my work, make sure that this structure is really consistent in every way, right, with the structure. So one of the things I might think about is the chemical shift. I knew that this was an isolated ethyl, but I didn't really think about the chemical shift before this. So I'm going to go ahead and confirm that, right? So what I know about benzylic hydrogens is that they should be around 2.5. So that's pretty consistent. So that is likely to be benzylic or right next to the aromatic ring. So it all looks good to me, and we'll move on to the next one. All right, one more practice problem. Remember, you're going to complete the 5-step process and see if you can come up with a complete structure. Take your time, pause the video, do the best you can, and then we'll talk about how to do it. Okay, so I calculated HDI and I got 1, right? So this means 1 pi bond or 1 ring. So that's something good to think about. When I have 1 pi bond or at least 1 pi bond and I have some oxygens, right? 1 or more oxygens, I'm thinking maybe my 1 pi bond could be a carbonyl, because carbonyls, again, in structures are very common. So if you have at least 1 oxygen and an HDI of at least 1, maybe you have a carbonyl. So it's something good to think about in the back of my mind. And then I want to consider the number of signals in integration and see if it matches the formula. So I'll count up the integration, right? 2, 4, 7, and it does match the number of hydrogens. So I don't need to worry about any more multiplication of the integration signals. Analyze each signal and draw fragments consistent with the signal. So over here, I might look at this signal. I would start with drawing CH3 because it integrates for 3 hydrogens. And then I see it's not split at all, it's a singlet, so it doesn't have any neighbors, good to know. And then what about the chemical shift, right? At around 2, a little bit higher, maybe 2.2, something like that. That's very consistent with it being next to a carbonyl, right, at around 2. So I think I'm going to go ahead and draw a carbonyl potentially next to this methyl. That would make no neighbors because there's no hydrogens attached here. It would make the chemical shift make sense, right? And so I'm really liking that as a fragment. Plus I had it in the back of my mind that we probably had a carbonyl. So something to think about. Okay, moving on to the other signals here. They're kind of, in a lot of ways, identical signals. Right? So it's almost like you can analyze them together when they're identical. What do I mean by identical? Very similar chemical shift, the same exact splitting pattern, and they integrate for the same thing. So I would start with drawing a CH2 because it integrates for 2 hydrogens. I would look at the multiplicity and see, okay, it's a triplet, which means it has 2 neighbors, right? So next to my CH2, I'm going to write CH2, right, because I have 2 hydrogen neighbors. And then I'm going to think about the chemical shift. At around 4, maybe it's next to something electronegative. So what do I have that's electronegative? Well, I have both a chlorine and an oxygen, right? So between the 2 of them, I would say it's much more likely that the more downfield signal is next to the oxygen, so here, and the more upfield signal is next to the chlorine. And that's just because I know that chlorine shifts 2.1, right? And having an oxygen, for example, of an ester, next to a shift at 3.0. So the shift is just greater for oxygen compared to chlorine. So that's why I think that this would match with this CH2, and that the CH2 next to the chlorine would match with this one. So sort of putting that all together, I was able to come up with this structure. You would want to double check that everything matches, including and most importantly, the chemical shift. So one of the things I did to see if the chemical shift matched or not was to do a quick little prediction. So for this CH2, it's a methylene, so it has a baseline value of 1.2. I'm next to the oxygen of an ester, so I'm going to add 3. And I'm beta to a chlorine, which is going to be the 1/5 rule. So 1/5 of 2.1 is about 0.4. So I'll go ahead and add in 0.4, and I'll get 4.6 ppm total. For this CH2, now I am alpha to a chlorine, so I'm shifting 2.1 from my baseline value of 1.2. And then I'm also adding in the fact that these hydrogens are beta to the oxygen of an ester. So the alpha shift when you're next to the oxygen of an ester is 3.0. So 1/5 of 3.0 is 0.6. So adding that all together, I've predicted about 3.9. This looks to be really close to really 3.9, so very good prediction. This was predicted to be at 4.6. This looks a little bit more like 4.4 to me, but again, it's within reason. And it can be, it can be off of your predictions. Don't get too married to, it has to be exactly where the prediction made it seem like it should be. Okay, let's talk a little bit about carbon-13 NMR. Carbon-13 NMR, while important, is not nearly as important as proton NMR. Proton NMR gives us by far the most information and can be very, very helpful in figuring out if we have the structure we think we have. But carbon-13 NMR is somewhat useful as well, and we're going to talk about that. One of the reasons why it's a little bit more difficult to deal with is because only carbon-13 nuclei are NMR active. And carbon-13 only accounts for about 1% of carbon atoms in nature. So our signals are not going to be very strong because yes, we have, billions of molecules in the test tube, in the NMR tube, but only 1% of the carbons are actually carbon-13. So there's going to be a lot more noise, right, or a higher signal-to-noise ratio. So the proton NMR is really nice because you don't need a lot of material because by far the most abundant isotope of hydrogen is just the simple nucleus with 1 proton in it. So all of the signals are strong here. But for carbon-13 NMR, the signals are not very strong. So how do we get around that? One of the things we can do if we're fortunate enough to have a lot of material and our product is a liquid, we could just take a neat sample. So basically, don't use any solvent at all. Because there's more sample, there's going to be a higher signal, which is helpful. But if your product is a solid, which is very common, then you're going to need to dissolve it to take an NMR. But you would ideally try to make the solution as concentrated as possible, meaning dissolve as much of the solid in the solvent as you possibly can so that you get more signal. If you're not fortunate enough to have a liquid or to have the ability to have enough material to make a concentrated sample solution with a deuterated solvent. Then you're going to need to a very sensitive receiver coil, and you're going to need a lot of time. Basically, you have to run thousands of scans potentially and average them all out to get a good enough signal to noise ratio that you can actually see or distinguish the signals from the noise. So sometimes people run NMRs, overnight or for 24 hours. You could even run it for a week, right, and do, thousands of scans if you really, really needed to. But obviously it's good if you can avoid that. Okay, another thing to think about with carbon-13 NMR is that what we're going to see is all of the signals are going to be singlets. So there's no multiplicity or splitting pattern to worry about like you do with proton NMR. So we're able to get splitting and integration and things like that from a proton NMR, but we're only really able to get shift information and the number of signals for carbon-13 NMR. So splitting and integration are not important in carbon-13 NMR. And here's the reason why. Integration is almost impossible because remember that randomly certain carbons will be carbon-13, but it's not like you have a molecule where all the carbons are carbon-13. So relative integration is very difficult to achieve there. And then splitting. We do what's called a decoupling process to avoid seeing splitting. Why do we do that? Okay, because basically if the neighboring hydrogens, right, were splitting the carbon-13 signal, there would be hydrogens attached to the same carbon, there would be the hydrogens attached to the neighboring carbon, there's potentially tons of hydrogens around splitting the carbon signals. Remember that the carbon signals are already weak, right? So splitting an already tiny little signal with into multiple peaks is bad. It means that we'll almost never see the signal. It'll just completely mix in with the noise. So the decoupling process, the way that works is at the same time as all of the hydrogens in the molecule are irradiated. So meaning they do a big pulse, a constant pulse of all of the RF frequencies that will resonate the hydrogens, such that all of the hydrogens are in the beta state. And then they pulse the RF frequencies that resonate the carbons. So essentially there are no neighbors, even though there are neighbors, right? Because all of the neighbors are in the beta state. So there's no difference. So you don't split a peak into two if the neighbors are all the same. So that's the way that they decouple it. And that just means that all the peaks are singlets, right, are just one signal peak. But that's good because that means we can actually, they're a little bit taller, we can see them more easily. Okay, let's see, I talked about that already. Compared to TMS, the chemical shift for carbons are different than for protons. Remember, it's common to see shifts from TMS between 0 and 10 ppms for proton NMR. For carbon-13 NMR, it's going to be between 0 and 220 ppm. And the difference is it's because it takes a different RF frequency to resonate carbon than hydrogen. Each signal in the carbon-13 represents a unique type of carbon. And when you have symmetry, there can be multiple carbons that are equivalent. So just like with hydrogens that are equivalent, we can have carbons that are equivalent because of symmetry operations. So you can analyze your structure, think about how many unique carbon signals are expected based on they're actually different. There's no symmetry operation that makes them equivalent. And then that's how many signals you should see in the carbon-13 NMR. Let's look at an example. Do you remember those xylenes, ortho, meta, and para-xylene? We can also analyze those by carbon-13 NMR. They were distinguishable by proton NMR, but they're also distinguishable by carbon-13 NMR. Remember those symmetry operations? for ortho, meta, and para having 2 different planes of symmetry. And then we can look at the carbons themselves to see how many signals are expected in the carbon-13 NMR. Remember, with the proton NMR, we expected 3 signals for ortho xylene because there's the hydrogens here, here, and here created the 3 signals. This carbon doesn't have any hydrogens, so there would be no signal in a proton NMR. But for a carbon NMR, we would see a signal because then we're looking at the actual carbon themselves and it doesn't have to have a proton attached. So there are 4 unique carbons in orthoxylene. There are 5 unique carbons in metaxylene and only 3 unique carbons in paraxylene. So the number of signals you would expect in each of these carbon-13 NMRs is different. So that would be a way to tell which one you have. Okay, what about that chemical shift, right? We said that we do get some chemical shift information from carbon-13 NMR. Only it's not very, there's a lot of overlapping between the regions where certain carbons can come. So this is kind of a simplified model of where to find certain carbons. There certainly can be outliers where they're slightly, to the left or right of their particular little box here. But this is a good generalization for carbon-13 NMR. So from 0 to 50 ppm, that's where we're going to find our sp3 hybridized carbons. And those are the ones that are not attached to an electronegative atom. So they're likely attached to other carbons or hydrogens. From the region of 50 to 100, that's where we're going to find sp3 hybridized carbons bonded to an electronegative atom, such as nitrogen or oxygen, right? Remember that nitrogen or oxygen being electronegative shifts signals downfield, and the same is true for the carbon-13 NMR. So it makes sense that they're a little more downfield. And then also sp hybridized carbons come in this region as well. From 100 to 150, those are our sp2 hybridized carbons, so either part of an aromatic ring or potentially part of an alkene. Remember that there's some anisotropy here that's causing deshielding, which is what causes it to come more to the left or more downfield on the spectrum. There is some anisotropy going on here for the triple bond, but there's 2 pi bonds, and they actually are orthogonal to one another, so the anisotropy is somewhat canceled out over here, which is why it's not as downfield. And then carbonyl carbons, like for many different functional groups, right? These are very common in organic molecules. Those are going to come the most downfield because, again, the presence of a nearby electronegative group and the anisotropy, right, of the pi bond will cause it to be the most downfield, anywhere from 150 to around 220. And that's really all the information we can get from carbon-13. So carbon-13 is not used as like, here's a carbon-13, analyze the spectrum, tell me exactly what the structure is. That's usually not the way it works. It's more like it's given to you in addition to a proton NMR, and you just use it to confirm the product after you've done all the assignments for the proton NMR spectra. You can use it to ask yourself how many unique carbons are in the structure. That can give you information on symmetry. Like if you have, 10 carbons, but you only have 7 signals, then you know that 3 carbons are equivalent. So that can give you some information as well. Chemical shift information can tell you whether or not you're likely to have a ring or a pi bond, a double bond in your structure, whether or not you're likely to have a carbonyl. So it can give you some hints as well to the structure, but typically we don't just use it to assign a structure by itself. And then I just wanted to talk a little bit about MRIs. So maybe some of you guys have had an MRI in the past. It's common, like if you have knee injuries, to get an MRI of your knee or something like that. I've personally never had an MRI, but maybe, I'm sure some of you guys have. And did you know that MRI stands for magnetic resonance imaging? And basically what an MRI is an NMR of your body. And there's a reason why they don't call it an NMRI, a nuclear magnetic resonance imaging, even though that's totally what it is. Some fear around the word nuclear and whether or not that involves radiation, which it definitely doesn't. And so basically it's an NMR spectrometer, but it gives an NMR in 3D, essentially. So, and things are color-coded based on proton density. So certain things in your body are very proton dense, right? Things like water obviously have a lot of hydrogens. It's not an organic molecule, but it still has hydrogen, so it's gonna be NMR active. And fat as well has a very, given the, the space, it's very dense in protons. So different tissues have different concentrations of protons, and the image is basically like a color-coded image where you can see different tissues and things like that. And so this is a picture of, I think like a disc hemorrhaging the spinal cord, or I don't know. I'm not a medical doctor, but I'm pretty sure that's what it is. So kind of interesting to note that maybe you didn't know what NMR was before this, but maybe you've actually had an NMR taken of your body. All right, so that is it for the lecture. Please let me know if you have any questions.